Greetings everyone, this is Mr. Mullen. On this podcast I'm going to talk about relative velocity. First off, I want to just kind of recap for us a free fall versus a horizontally launched projectile. So I'm just going to play this a couple of times. So when I launch a projectile horizontally, I'm going to kind of go that one more time. Play that one more time for you. So what you're noticing is the little lines in blue at the top are just showing what an object would be doing if there were no gravity, if it were just moving in a constant velocity in the horizontal direction. The red dotted lines are showing what an object would do if it were just freely falling, and the purple is showing the result of both the horizontal constant velocity motion and the vertical free fall acceleration occurring at the same time, and there's our little parabolic trajectory. So as we saw with projectiles, the vertical and horizontal motion were independent of each other. The next thing I'd like you to look at is I've got a little simulation here called the Riverboat Simulator, and so I'd like you to kind of make some predictions. The first thing I'm going to do is I'm going to I have a way that I can send a riverboat across a river, and I can adjust on the right hand side how fast the river's flowing. I can also adjust how fast the boat is going and the direction the boat is heading. So the first thing I'd like you to do is predict for me if I were going and sending my boat. I'll actually send it in the southward direction. Let's say I send my boat south going 7 meters per second, and it is in a river that's moving 3 meters per second. Really fast, make a prediction of what you think the final velocity of the boat will actually be. Okay, I'm going to go ahead and show our velocity, press play. And so when I go back and I look and see what actually happened, it's kind of hard to tell, but it moved 180 meters in 18 seconds, which means it must have been moving 10 meters per second, which would have been the resultant of those two things. So just kind of showing you, just make a new little page here. What that might look like, we had I was going the other way. Okay, I was going 7 meters per second, tip to tail. I'll add the 3 that I got from the river, and so our resultant was 10 meters per second for the object. Okay. If I were to send the boat in the opposite direction, let's say I reset that, and now I'm going to send it north at 7 meters per second, but the river is still going 3 meters per second. Go ahead and make a prediction what you think is going to happen to the velocity. And when I go back and I do some math, I'm going to find that instead of going 7 plus 3 meters per second, it's going to be what I would expect if I had the opposite effect true. So I'm going north 7 meters per second, tip to tail, but I'm going 3 south. My resultant would be 7 minus 3, or 4 meters per second. So we saw vector addition, we saw how that worked out in one direction. Now I'd like you to predict if I were to send the boat across a river that is not moving at all. I'm going to go ahead and show you that now. Okay, so it's going across the river. If I were to turn on the current, I'd like you to predict what you think is going to happen to the amount of time it takes to get across. So I just kind of did this little simulation here, and I'm going to go ahead and put my velocity all the way up here. I have a dot going, I have a dot going every single second. So I send this across, and our time was 4.0 seconds to get across the river. I'd like you to predict what's going to happen if I turn on the river going 3 meters per second. What's going to happen to the time to get across? So it looks like there's some little vectors on here showing velocity of the boat, velocity of the river. It actually gives me the total or the resultant. But when I press play, we're going to see that even though it was being propelled downstream by the river, when I look at that time, it's still 4 seconds. It was the same. So what does this mean? It means that the vertical velocity in the y direction from the river had no effect on the horizontal velocity across the river, just like with the projectile. It's only a little bit easier than projectile problems because both x and y directions have constant velocity motion. Alright, so that brings us to, we're going to go ahead and do a couple little example problems here. Relative velocity, this is in our notes handout, so if you guys could take that out. For us, I think this is, it might not be number 20 because I had the order changed, but it's going to be the last couple problems in our handout. So as we're taking out that, I want to kind of draw a little picture of what's going on. So we're going to go ahead and use our draw feature. Don't know why I can't draw on this, so I'm just going to copy this into OneNote, because I'm not going to record this video again. Alright, here we go. Alright, so first question, I put a river in a boat and pointed it directly across and row for 100 seconds, and in still water, I can row my boat at 3 meters per second. Fortunately, when you reach the far shore, you realize that you're 160 meters downriver from where you thought you would land. So the first thing I'm going to do is I'm going to draw a little picture of what this situation is going to be looking like. So here's my little river here. I'm going to draw my river, and I start out and I head off to try to cross the river. And I'm going 3 meters per second. And I go across the river, and when I get to the other side, I realize that I'm actually 160 meters down river from where I thought I was going to be. So there's my 160 meters. So as I went across the river, I had a little delta x, and as I went down the river, I had a little delta y. Now for the simplicity's sake, I'm going to make down the river be the positive direction so that my displacement was positive. And that's totally okay, we can do that. Alright, so what I have here is I want to know how wide the river is. I want to find that delta x. I want to know how far I actually traveled overall, and then I want to figure out how the time compares to the river crossing. So in order to solve this problem, I'm going to need to divide up my motion into the x direction motion and the y direction motion. Okay, we're going to separate those two just like we did in our last problems that we solved. So in the x direction, I'm going to be rowing my boat as fast as I can, and that's going to be 3.0 meters per second in the x direction. It looks like I'm rowing for 100 seconds. So our change in time would be 100 seconds. And I want to know how far I was able to go, how far across the river it was. So that 3 meters per second we saw just a moment ago is going to be constant for this boat going across. So to find that delta x, I can use my equation for constant velocity in the x direction. And when I do so, I'm going to take my 3 meters per second times my 100 seconds, and I'm going to get that the river must have been 300 meters across. Right? So there's how wide is the river? X direction motion is going to be determining how long across it is. The next question is asking how far have you actually traveled. So when I look back at the situation here, I actually ended up down here. So my displacement, put on here displacement, what does that look like? I went in this direction 300 meters, I went in this direction 160, I want to find how far I actually went. So when I do tip to tail, I can use my Pythagorean theorem to find that displacement. And to find that, I'm going to take the square root of 300 squared plus 160 squared. And I'm going to find that that total displacement was 340 meters. It's going to be the overall displacement here. So that was 340 meters. River was 300 wide. Okay. Now that was all for x direction stuff. I was able to figure all that out. For part C, how would the time to cross compare if the river were to stop flowing? That's going to be same time. The time would be the same. Horizontal and vertical motion, x and y, were independent of each other. So I hit the shore after rowing 300 meters after 100 seconds. I'm still going to take 100 seconds to cross that 300 meters, going 3 meters per second in the x direction. Alright, question D says, how fast does it look like you're going relative to a person standing on the shore? So if I'm over here watching this go down, I see that you've made it downstream over here somewhere. How fast does it look like I'm going? I'm going to have to actually look at the total or resultant velocity of the boat. So I'm going to draw a miniature little triangle here. I was moving 3 meters per second to the right. That was my Vx. But I'm going to need to know how fast I was moving vertically in order to figure out my relative velocity. When I go back to this little boat problem and I kind of reset this here, I'm going to amp this up a little bit. That total, how fast it was actually moving, was depending on the horizontal and the vertical velocity at the same time. What was that? So I need to find the vertical velocity. So I'm going to go over to my y direction side and I want to find my y direction velocity, question mark. We're going to look for that. I know that it was going across the river for 100 seconds. The time was the same. My delta y, remember down the river I said was positive. We made 160 meters down the river. That's how far we traveled. And instead of using kinematic equations, we're not accelerating down the river. The river was moving at a constant speed. I know that my delta y is going to be equal to, actually I'm going to rewrite this just so we can see. My velocity in the y direction is going to be change in position over change in time. It's constant, okay? It was constant velocity. So because it was constant, I can go ahead and plug in to figure out what my velocity would be. My change in position was 160 meters. Took me 100 seconds. So my velocity would be 1.6 meters per second. When I go back and look at my little triangle over here, I can now use Pythagorean theorem to find the VR, and that's going to be right here, and that's going to be equal to the square root of 3 squared plus 1.6 squared, and that's going to be 3.4 meters per second. How fast does it look like you're going relative to a frog on a log in the river? So, hard for me, or imagine a little bit, if you're in the river, here's my riverboat problem. As the river moves, choose a spot on this river that you want to look at. I'll play that one more time. I'm just going to put my cursor over a spot in the river. So let's say I'm a frog. Let's say I'm over here in the river, right here. So here's my frog. Actually, I'll do it right here because it's a little easier to see. So from that perspective, as I follow down with the river, you'll notice that the boat was actually on the same plane with me the whole time. We'll do that one more time. So if I'm a frog in the river moving with the river, vertically I'm moving down the same that the boat's moving down. So what's going to happen is my vertical velocity then is going to be 0 relative to the, you're moving with the current, so we only see the x direction stuff. Put that down here. Only see x direction stuff. Alright, so how fast does it look like you're going relative of so 0 meters per second is the vertical, so that means all you see is x direction stuff, which is just going to be 3 meters per second. Okay, you're just going to see that object coming at you at that velocity, whatever it is. Okay. Alright, we've got one more little example problem. This is going to be for airplanes. It works just the same. Let's say you want to fly in a small plane from Columbus, Ohio. It gives a latitude there to Detroit, Michigan, which is exactly 160 miles due north. So I'm going to draw my little picture here. Here is Ohio, and I want to go up here to Detroit, Michigan, and I want to go, and that's going to be 160 miles due north. So I want to go ahead and I'm going to zoom this in just a little bit for us here. Now in still air, my plane can fly 80 miles per hour. So I point my plane north and I take off. Unfortunately, there's an 18 mile per hour crosswind blowing from west to east. So from west to east, so we've got a crosswind blowing for our plane here. And as it's blowing, I would land in Detroit, but I'm not going to land in Detroit. I'm going to land somewhere over here. Okay, so we've got, latitude, longitude. We've got a grid system here. I'm going to land somewhere over here, and that's what we're going to try to figure out what that distance is going to be here. So I'll put on here delta x. All right. So what I need to do, if there's no wind blowing, how long would it take for you to get from Columbus to Detroit? So no wind blowing. I'm going to go ahead and break up my problem again into x and y direction. Beautiful. So to get with no wind blowing, I'd be going in the y direction. My vertical displacement would be 160 miles. I'm going 80 miles per hour, and I'm pointing my plane straight north. So my Vy is 80 miles per hour. And then I can go ahead and figure out what my change in time is. Question mark. I'm not going to use the kinematic equation because I was not accelerating. So I'm going to use my equation for constant velocity. Displacement is equal to that constant velocity times the time. And so if I'm going 80 miles per hour times 160 miles, oops, let me take a step back here. If I'm going 160 miles and I'm going 80 miles per hour, I can solve for delta t, and my units left are going to be hours because I've got miles per hour. My miles will cancel. I'm left with 2 hours to get to Detroit. Okay, so that's if there were no wind. Now, even if there's a wind blowing in the x direction, that vertical motion is going to be independent. So it's still going to take me 2 hours to get to that latitude, that far north. But because I'm also moving horizontally, I've got to worry about being blown to the right. So how long would the wind blowing? It's going to take 2 hours. With the wind blowing, how long would it take you to get to 42 degrees latitude? That's up here, 40 degrees north. That's going to be the same kind of vertical position. It's still going to take me 2 hours to get that far north because that vertical motion is not going to be affected by the horizontal wind. Well, next question says, with the wind, how far east of Detroit do you actually end up? Okay, so the wind is blowing in the x direction at 18 miles per hour. That's going to be the x velocity given to the plane by the wind. I want to find out how far east of Detroit I actually end up. So that's going to be my delta x. I know that the time that I'm traveling in my plane is 2 hours. And I can use my little equation, delta x is equal to v sub x delta t. I'm going 18 miles per hour for 2 hours. We're going to be looking at 36 miles. Okay. 36 miles. Alright, last couple problems. How fast does it look like you're going relative to a person standing on the ground? So if I look at someone standing on the ground over here, let's say I'm watching this plane go by. I see them going north at y velocity was 80 miles per hour, and I see them being blown to the right at 18 miles per hour, and so I can find that hypotenuse is going to be the square root of 80 squared plus 18 squared. That's going to be 82 miles per hour. How fast does it look like you're going relative to a dude in a hot air balloon? So as I'm watching this plane kind of do its thing, here's my plane flying along here. It's moving north, it's moving east. I'm actually seeing it go this way. As I'm in a hot air balloon, I'm going to be moving along with the wind as the plane is getting closer and closer, and that person, that hot air balloon is moving with the wind, is only going to see the y direction stuff. So 80 miles per hour is all that person in the hot air balloon is going to see because he's moving with the wind. So they both have the same horizontal stuff. He's going to watch that plane coming straight at him. Alright, this has been a little podcast. I hope this has been helpful. You're now able to do the rest of Motion in 2D worksheet, and we'll whiteboard this thing tomorrow.